Okay, so in this example, we have acetylene being hydrogenated to form ethane. And this is like practice with using limiting reactants and like figuring out excess, and then also like the yield ratio and whatnot. So part A asks us to calculate the stoichiometric reactant ratio and the yield ratio. So first we want to write out our reaction, and that is going to be C2H2 plus 2H2 is equal to C2H6. So we know that, so we're trying to figure out the moles of H2 that react per mole of C2H2 that react. So this is our stoichiometry. We have 2 moles of H2 per mole of C2H2. So it's 2 moles of H2 that react per mole of acetylene that reacts. So that's the first thing we were asked to find. And then we also want the yield ratio. And the yield ratio is going to be the moles of ethane formed per mole of hydrogen that reacts. So there's 1 mole of ethane formed per 2 moles of hydrogen that reacts. So 1 over 2 is going to be 0.5. So we have 0.5 kilomoles of C2H6 formed per kilomole H2 that reacts. Okay, now for B, we're asked to determine the limiting reactant and then calculate the percentage by which the other reactant is in excess. So we're actually given in the problem statement that the feed to the reactor contains 1.5 moles of hydrogen per mole of C2H2. And we know we need 2 moles of hydrogen per mole of C2H2. And so since the moles of hydrogen per mole of acetylene is equal to 1.5, and it's required that we have 2 moles of hydrogen per mole of acetylene, we know that hydrogen is limiting. So then we identified the limiting reactant. Now we want to calculate the percentage by which the acetylene is in excess. So we know that we have 1.5 moles of hydrogen fed. So then we have 1 mole of acetylene fed. So the acetylene required for 1.5 moles of hydrogen fed would be 0.75, since for every mole of acetylene you need 2 moles of hydrogen. So it would just be half of however many moles of hydrogen we have fed. So 0.75 moles of acetylene required. And this is our theoretical. And then now we can figure out the percent excess of acetylene. Is going to be equal to how much we have fed minus required over required. So we have 1 mole of acetylene fed, 1 mole fed, minus 0.75 moles required over 0.75 moles required. And so then I'm gonna multiply that by 100. So then that ends up giving us that we have 33.3% excess of acetylene. Now for part C, we want to calculate the mass feed rate of hydrogen required to produce 4 times 10 to the 6 metric tons of ethane per year, assuming the reaction goes to completion and that the process operates for 24 hours a day, 300 days a year. So we're just figuring out the feed rate required given a certain production rate, and also given a certain amount of downtime to the process. So we want 4 times 10 to the 6 tons of ethane per year. And so for our purpose, 1 year only has 300 days because we're only operating 300 days of the year. And then 1 day has 24 hours. 1 hour has 3,600 seconds. So we've got our units of time in terms of seconds. Now we just need the tons of C2H6 turned into kilograms of hydrogen. So 1 ton is equal to 1,000 kilograms. So we've got our ethane in terms of kilograms now. And now we want it in terms of kilomoles. So there's 30 kilograms of C2H6 and 1 kilomole of C2H6. That's just the molecular weight. And I'm gonna continue down here. And then our stoichiometric ratio, we have 2 kilomoles of hydrogen per kilomole produced of ethane. So 2 kilomoles of H2 per 1 kilomole of ethane. And then there are 2 kilograms of hydrogen in 1 kilomole of hydrogen gas. And that ends up giving us that ends up giving us 20.6 kilograms of hydrogen gas per second for this given production rate of ethane and this amount of operating time.